Hello everyone. Uh, my name is Fran. My name is Fran, Sucic. It's pronounced Sucic. You don't have to bother with that. Just you can call me Fran. And I'm going to be giving a course here on YouTube in Ramsey Theory. Uh, okay. So first, uh, I'll tell you I'll tell you in general terms what Ramsey theory is all about. In the simplest possible terms, it's the theory of finding irregularities and patterns in otherwise completely random systems. So it's finding regularity in structures or substructures of a completely arbitrary system. You may have heard of Ramsey numbers, and we're gonna touch upon that, but that's not gonna be the main focus of this course. The main focus is gonna be Ramsey theory. Okay, so first let's go through some technicalities. So I'm gonna give you my email. Uh, I'm gonna give you my email, so you can send me questions if you have any of them. Um, and I'll do my best to answer them in a satisfactory manner. And also, you can ask me anything about the course or in general about the mathematics related to the course. And also, if you want answers to the exercises I'll be giving out, you can also contact me for that. Uh, okay, so a little bit about me. I am not a professor or anything like that. I am a recent graduate from Cambridge University, and I thought this would be a nice, fun little project to do over the summer. Well, it's COVID time, so I can't really do much. Uh, so I thought this would be a nice way to, fill up my time and do something maybe useful to some of you, if you're interested in this sort of thing. Okay, and the resources for this course, I mean, books and such, unfortunately, there aren't going to be any because I don't really have a good book to recommend. It's going to be very much a self-contained course, so uh, uh, you won't have to look up anything anywhere else. You're just going to have to watch the lectures and see if you know, you're just gonna have to watch the lectures and uh, ask me if you have any questions. Um, okay, and now I'm gonna talk about the prerequisites for this course. So I chose this course because basically it has no prerequisites. It's sort of, many people say that Ramsey theory is a branch of combinatorial mathematics, and perhaps it is, but some people think it's a separate field in its own right, and and I do believe, and I do side with those people. I do think it's a separate field of mathematics. It's not really combinatorics, but it's very, very well connected and intertwined, and it's intertwines with combinatorics. Okay, uh, so there aren't any prerequisites for this course, except for maybe one thing, and that is going to be uh, late undergrad or graduate graduate uh, maturity in mathematics. Okay, so you don't need to know analysis or any sort of that thing. You basically need to know induction and like a lot of logic. But uh, you, well, it isn't a course for somebody just starting mathematics. It's for people who, are used to the mathematical language and used to mathematical reasoning. So I wouldn't recommend this as a starter course. So this is the only prerequisite. And I also chose this topic because, well, there doesn't seem to be many people on YouTube covering this. Um, okay, uh, so we can now basically start with the lecture. Hmm. Just excuse me while I find my notes. I didn't open them before. Okay. Uh, so so this course is gonna have two parts. It's gonna have part one. Part one is gonna be uh, monochromatic monochromatic systems. Okay, and part two uh, it's gonna be partition regular equations. So this first part, uh, it's gonna be it's gonna be a theoretical background to Ramsey theory. We're gonna define everything. I'm gonna show you what I mean by finding sense and substructure and regularity and totally arbitrary systems. And we're gonna make that concrete. We're gonna make that mathematically concrete. And then in the second part, after we've done all this theory, in the second part we are going to apply this to really prove some fascinating results, some things that are really unexpected. In particular, the epitome of this part is going to be Rado's theorem. Rado's theorem, and of course, Rado was a famous combinatorial mathematician, uh, and he did many things, but among them, this is, let's say, one of the more famous results Rado ever did. Okay. Uh, ta, 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 ta. Okay, so let's get into it. Chapter 1. I think it would be useful for you to write down everything I am writing down, and perhaps a bit more on things you find unclear, or the things I'm going to say and which I'm not going to write down. Uh, yes, I think it's sort of the best way to learn mathematics is to, listen to me talk about this, give you the spiel, and then later look at your own notes and try to understand it in your own terms. Then maybe come back to these lectures and see if your understanding agrees with what I've said. It's all about creating your own uh, intuition. Okay, so monochromatic systems. I'm always in this course gonna write uh, the symbol n for the natural numbers. Okay, so this is gonna be the natural numbers, and I'm also gonna use the notation uh, this notation for the set of all positive integers up to n, where n is some natural number. Okay. So this is, common notation. I hope you've seen this before. Okay, and also we're gonna define what a we're gonna define a shadow or a layer of a set. So for set x and a positive integer r, we define x, the rth layer of x, to be all the subsets of x such that they have size r. Okay, so for example, uh, n2 would be all the pairs of numbers, all the pairs of numbers, all the pairs of natural numbers. I'm just gonna write it like this. That's 311. Well, all the possible pairs. Okay. Uh, okay. Now we're gonna define what a coloring is on. We're gonna define what a coloring is. Okay. So first, imagine N2. What is this? What is this? Well, these are all the pairs of natural numbers, but we can very easily visualize this in graph theoretic terms. So this is 1, this is 2, this is 3, this is 4, this is 5. And if we connect every vertex in this graph by an edge, we can see that every edge corresponds exactly to a pair of natural numbers, So this edge is 1, 2, this edge is 1, 3, this edge is 1, 4, and so on. This edge is 3, 4, and this edge is 4, 5. So basically we can visualize this set by considering this graph where the edges are elements of this set. Okay, there's a clear bijection between these two. Okay, and then we can define a coloring, a 2 coloring, from as a function from n2 to, red, blue. We can color all of the edges either in red or blue, and of course this is equivalent in every way to the set 1, 2, homeomorphic. If you, well, we don't have a topology, but there's a bijection and uh, clear equivalence between these two sets. Okay, so we have our natural numbers, and we connect them all by edges, and every edge has a color. Every edge has its own color. And what can we deduce about this system? So we see that this system is completely arbitrary, and by that I mean the coloring is completely, given a coloring, uh, we don't know anything about it. So the coloring is completely arbitrary. So what can we say about the the colors of the edges in this system? And surprisingly, we can say something, and something that is actually quite meaningful, and that has, direct consequences. Uh, so the question is, well, I've already answered the question, but can we find an infinite monochromatic subset of the natural numbers? And by that I mean, can we find subset of n such that uh, C restricted to M is constant, so that can we find a subset of n, for example, 2, 5, blah, 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 whatever, which is infinite, M infinite, such that C is constant on M. That is, every edge, uh, every edge in M is of the same color. So the edge between 2 and 5 is red. This is also red. Every possible edge is red. Now this is a non-obvious thing. This is a non-obvious thing for an arbitrary coloring, of course. Uh, so first we're gonna look at a few examples. First we're gonna look at a few examples, some concrete colorings. Okay, and uh, I'm gonna be denoting edges here with ij. And ij and I and j are two natural numbers, and we're always gonna assume written this way that I is less than j. So the edge 4, 5 is this edge. The edge 7, 10 is gonna be, I hope that this is 7, 8, 9, 10. Okay, so that's how we're gonna uh, denote edges. And now, okay, now uh, let us color the natural numbers uh, in the following way. Color the edge ij red, red if I plus j is an even number. Color ij blue if I plus j is an odd number. And now, can we find an infinite monochromatic subset of n? That is, can we find an infinite subset of n such that each edge in M is of the same color? You can pause the video now and try to think, try to think of an example for M. Okay, and in fact, yes, this is very easy to do. You just have to find a set such that all uh, the addition between every two pair is going to be an even number, and that's just, well, you can just choose the set of all, you can just choose the set of all even numbers. So, yeah, yeah, that's it. Okay, so in fact, there is an infinite monochromatic set M in this situation for this coloring. Okay. That's a very easy and basic example. If you want to do odds, if you want to do odds, let's see. Well, no, that's a bit more complicated now, is it? That is a bit more complicated. Well, have a think if you can even do odd. I'm not sure at this moment. Okay, now let's do example number 2. Example number 2. Color ij, uh, color ij. Again, red doesn't really matter. It's just a placeholder. Uh, if let's see, what do I have here? The max. You know what the max function is, the maximum of a set. Of course, it's going to be a finite set, so we're not going to have infinities or anything like that. The maximum integer n such that 2n divides a plus g, a plus j, and such that this maximum is an even number. And the blue and blah blah blah, the same thing if this is odd. Okay. Now again, pause, please pause and try to think of the example on your own. Uh, this is how I'm gonna denote infinite sets, by the way. I'm gonna just put infinity in front of the set. You know, please excuse me for my horrible handwriting, but it's really hard to use the stylus and not have an effed up handwriting. Okay, so have a think about this. Uh, if you have two numbers, you take their not you add them together, and what if the number is odd? Well, then it's zero. Zero is gonna be um, it's gonna be this maximum is gonna be zero. And that's even, that's fine, but maybe we shouldn't play around with odd numbers because, we want to get even stuff. And if the number is even, then it's fine. Uh, if the number is even, well, one or two things can happen. The the n can be even or odd, so that doesn't give us anything. So we can't look at just even numbers. We got to do something more. Uh, but if we just look at numbers of this form, so numbers of this form, numbers of this form, what can we do? Well, we can factorize it. We can factorize it into, something like this, and we're gonna get exactly, we can always exactly determine the n very easily. Now we see that this is a problem because this was raised to an odd power, so we quickly see that m is then the powers of 2 just raised to an even power, power, yes. Uh, okay, so this works. You check it if you haven't thought of it. Okay. Example number 3. Now this example is gonna be a lot harder than the previous two. So color ij red if uh, if I plus j has an even number of prime factors. Okay, and of sorry, distinct prime factors, and color it blue if I plus j has an odd number of distinct prime factors. So let's have a look at a few numbers. By the fundamental theorem of arithmetic, every number has a unique prime factorization. So, look at 10. That's going to be 2 times 5. So this guy is going to have an even number of distinct prime factors. Then look at 16. That's 2 to the fourth, just 1. So This is going to be an odd number of distinct prime factors. And now try to think of I'll give you a few moments, and try to think of an infinite subset of n such that it's monochromatic. Uh, such that, you know, not the set itself, but M2 is monochromatic, i.e. this function is constant. C restricted, how can we write this? C restricted to M is constant. Okay. Uh, don't try too hard because, well, because nobody has ever actually solved this. But we do know that such a set exists. We do know that it exists, but nobody has ever found it. And this is because, you know, prime numbers are basically complicated, and we don't, and we're not dealing with prime numbers here. We're dealing with two numbers, and when with two numbers, and not their prime factors, but the prime factors of their addition. I don't, you know, not their product, but their addition. Okay. Uh, and that's really hard. That's a really hard problem because think about it. You know absolutely nothing about the prime factors of I plus j, even if you know I and j. So, you know, 10 plus 6 gives you this. And how can you deduce anything about the prime factors of this uh, with knowing the prime factors of this? It's just a complete nightmare. So, yeah, it's a complete nightmare. Okay, but we do know that such set exists, and now we're gonna prove why we know. Now we're gonna prove that. So the first theorem of the course, it's gonna be theorem 1, 1.1, because this is the first chapter, and it's called Ramsey's theorem. So I'll say a few words about Ramsey before we get into the theorem. He was, well, basically Ramsey was a wonder kid. He lived at the beginning of the 20th century, and he died at the age of, I don't know, 24, 25, 26, something like that. And by that age, he already managed to do a lot of things. If you know anything about philosophy, he was friends with a famous philosopher named Wittgenstein, you know, the Tractatus Philosophico, and he was actually the first person to translate it from German to English. So, and he was also at Cambridge uh, along with Wittgenstein. So he was an impressive young man, but unfortunately, due to liver-related problems, he died very young. So we didn't get to see, you know, his full potential. You know, something like Ramanujan or Galois, if you're into that sort of romantic maths uh, thing. Okay, so let me state the theorem. So let C be an arbitrary coloring of N2. Okay. Then there exists there exists uh, an infinite monochromatic set, call it M, a subset of the natural numbers. So for any coloring, there exists an infinite monochromatic set M, such that the coloring, yeah, an infinite monochromatic set M, i.e., oh shit, i.e., okay, i.e., C restricted to M is constant. Well, actually not to M, but to M2 is the second layer of M is constant. Okay. And how are we gonna prove this? How are we gonna prove this? We are gonna prove this by sort of an easy argument, but a very deep argument. That's what I'm gonna say. Because we're gonna prove it by induction, and we're sort of gonna do uh, two inductions. We're sort of gonna do, oh, well, not two inductions, but two pass. It's called a two-pass induction. Uh, two-pass proof because I'll explain it later. So let's visualize this. Let's visualize this over here. So we've got our natural numbers, going along like this. And well, let's start somewhere. Let's start somewhere. Let's pick an element of the natural numbers. Pick A1. Okay. So let's say we pick this guy. We pick this guy. This is A1. And A1 has an edge with every other natural number. So it has an edge with this guy, it has an edge with this guy, so on. And these edges can be either blue or red. And it's not hard to see that there exists an infinite set of natural numbers such that all of the edges from A1 to that set are of the same color. Okay? And this is by the pigeonhole principle. Because if there was no such set, that would mean that there's only 30 vertices such that the edge between that vertex and A1 is red, and there's only 40 of them which are blue. And then what about all the other points? So by the pigeonhole principle, there exists such an infinite set. Let's call it B1. So, and let's write it down. There exists B1 subset of the natural numbers, but without our lone point A1, which we picked, such that uh, all the edges from A1 to B1 have color C1. Okay, we don't know what this color is. It may be blue, it may be red. We don't know. Let's just call it C1. Okay. Okay. Now, well, what can we do now? We've arranged so that everything connected to B1, so that every edge from A1 to something in B1 is of the same color. What can we do now? Well, we repeat the process. We pick an A2 inside B1. So pick A2, an element of B1, and repeat the process. So we don't know there exists a set B2 inside of B1 minus A2 such that all the edges from A2 to B2 are of the same color, say C2. Okay, and continue inductively. Continue inductively. Okay. Continue inductively. Thus, we obtain a sequence of points of natural numbers, a1, a3, and so on, such that every pair a1, every edge a1, an is of the same color, namely C2, C1. Every edge a2 to some an, where of course here n is bigger than 1, here n is bigger than 2, have color C2, and so on. And so this is C3, C4, blah, 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 blah. Okay, and now we again use the pigeonhole principle. So this is either red or blue, this is either red or blue, blah, 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 and so on. And we can now choose an infinite set. There exists an infinite subsequence of this sequence, which is monochromatic or constant. So we pick C1, C3, da da da, such that this is monochromatic. So uh, so there exists uh, an infinite sequence and J such that Cn1 equals to Cn2 equals to Cn3 and so on, meaning that A and 1, A and 2, of course these are all, ascending numbers, A and 3 are all, meaning that this set is infinite, and if you look at it, it's monochromatic because A and 1 and A whatever, this has color Cn1, okay? And Cn1 is, equal to every other color. And you pick A and J, A and I, okay, A and I, A and J has color C and I, has color C and I. And C and I is, it's the same color. So, well, basically we're done. uh, basically we're done because you pick any edge, it's gonna have this color. Perhaps blue, perhaps red, we don't know, but it's gonna have this color. And this is the end of the proof. Okay, now I'm gonna say a few things about the proof. So noto bene, I'm gonna be writing that for remarks. That's Italian for nota bene, which means, noto is a note and bene is good, so a good note. That's it. I don't know. It's it. I don't know. It's dumb. Uh, okay, so this is what it's called to pass. proof. Let's call it two-pass proof because we uh, we went through the natural numbers and we picked a subsequence of the natural numbers. Okay, and then out of that subsequence we picked another subsequence. So this is an infinite there's an infinite amount of steps happening here, and then after that infinity we also do an infinite amount of choices. So there's really a lot going on here in this induction. So we first do this induction and then we do this choice, and this is all uh, no, we never, well, we first pick this and then we pick this again. So this is we did an infinity of steps and then we did another infinity of steps. So that's why often it's called a two-pass proof. And as I said before, example 3, the one with the prime numbers, is unsolved. That's unsolved. So if we know that such set, an infinite monochromatic set exists, but nobody has ever found it. So if you want to try, go ahead. End up maybe you'll end up doing something fantastic. So why not? Okay. Uh, mm, okay. So your homework for today is to absolutely and completely understand this proof. It's quite simple. I don't think it's hard to comprehend, but you need to have it in your mind. You must be able to recall it and know the steps and completely understand them because we're gonna move on to different things, and and this is really the base on which all of those different things build on. So it's quite important that you understand that you understand the proof of this theorem. Next time I'll be showing first a few simple consequences of this theorem. I mean, not simple actually, things that are hard to prove on their own, but then they suddenly become very easy with this tool, which is uh, which is great because that's one of the signs that you've stumbled upon something really good because uh, it reduces complicated things to easy easy things. So thank you, and I'll see you uh, I'll see you next lecture.